continue with the next talk by Valentin Rapenne. He'll talk about the continuous linear operator associated with the HTTP model.
So thank you very much for the invitation. I am very happy to be here today to make this presentation. So today I will explain a work which has been done together with Christophe Sabot. And this work is about a continuous random operator which is associated with the H22 model and the vertex reinforced jump process. So I just explain briefly what will be the structure of the talk. So first, I will introduce some tools which will be important in order to define some random matrix G beta on a discrete graph, which is linked to the H22 model. And after that, I will explain the link between G beta and some other important objects like the H22 model and the vertex reinforced jump process. And finally, I will explain that we can construct a space continuous version of this object G beta, and I can describe it quite explicitly, and we will see that we can also describe the inverse of this random object. Okay, so first I would like to explain something about the inverse Gaussian distribution that some of you may know, and it will be useful for the sequel of the talk. So what is the inverse Gaussian distribution? It is just a distribution on R+, which has the following density. And you can see that the density decreases exponentially fast at infinity and at 0, and you have a polynomial term in the square root of t cube. And one can construct explicitly a random variable which has an inverse Gaussian distribution in the following way. I can pick standard Brownian motion B. I choose positive real numbers theta and eta, and I consider the drifted Brownian motion theta plus bt minus eta t. And if I define t as the first heating time of 0 by this drifted Brownian motion, actually one can show, thanks to Girsanov theorem, that it has an inverse Gaussian distribution with explicit parameters. Okay. So keep that in mind. Now I will explain something which seems to be different at first sight, which is the beta potential. I will define what it is. But in a few minutes I will explain the link between this first slide about the inverse Gaussian distribution. So we fix a graph V with n vertices, and we choose a weight matrix on this graph, Wij, with non-negative weights on the edges. I will assume that my weights are symmetric. Okay, during this talk, and we have also the property that Wij equals 0 if and only if Ij is not an edge of the graph. And I will fix a vector with positive entries theta and a vector with non-negative entries eta on the graph. And now, for every beta, which is a vector with non-negative entries on the graph, I define a matrix, which for now is deterministic, but in a few minutes it will be a random matrix. So this matrix is H beta, which is 2 beta minus W. So W is a weight matrix which has been defined before, and 2 beta, it is a diagonal matrix whose diagonal entries are 2 beta 1, 2 beta 2, etc. Okay. So we can see that as a kind of Laplacian, which has been perturbed on the diagonal part. And when H beta is invertible, so for big values of beta it will be invertible, you can inverse it, and when we can inverse it, we can define a matrix which is G beta. And keep this definition in mind because G beta will be the most important object of this talk. Okay, so and in the case we will consider where beta will be random, actually G beta will always be invertible. Okay. So with this definition, we can introduce a measure on RV, which is nu v W theta eta, which has the following horrible density. So you can see that I can comment the terms of this density. So you have the indicator of H beta being positive definite. So we knew that H beta was a symmetric matrix by definition, but we impose the fact that it is a symmetric positive definite matrix. And yes?
Maybe you should say it's the same that Margarita.
Yes, I would have said that in a few bits, but yes, it is exactly the object which has been introduced by Margarita this morning, and there will be other densities which will be the same as the object of Margarita, which has been introduced this morning. It is strongly, what I will explain is linked with what has done Margarita. So yes, we have the. Yes, Margarita explained that this morning. We have the indicator of H beta being positive, therefore the square root of the determinant is well defined. And we have this term of exponential of minus theta H beta theta and minus eta H beta eta. Okay, so one can define this measure, but actually it is a probability measure. It is not obvious at all at first sight. It has been proved by Sabo, Tares, and Zeng in 2015, and therefore, if you have a probability measure, it is possible to consider a random vector of beta with positive entries, which has this distribution nu v w theta eta, and we will call this random vector the beta potential. And first, let me do some remarks. So we can see that the density of nu v w theta eta is very similar. It looks like the density of the inverse Gaussian distribution, because if we go back, okay, not too bad. There you have, you can imagine that T is H beta. And so if you replace the inverse of positive real numbers by the inverse of matrices, you have something A squared times T, which is, we can imagine that it is H beta, and B squared divided by T, but you can imagine that it is B squared divided by H beta, so in some sense B squared times G beta. If you compare it with the density here, you have the formula which is quite similar in some sense, and the determinants can be understood as a polynomial term in the inverse Gaussian distribution. So if you look just formally at the densities, you have something which is very similar with the inverse Gaussian distribution. And actually, you can make this link rigorous, because for every site I in the graph, one can show that 1 divided by 2 beta I has an inverse Gaussian distribution. Therefore, one can understand the beta potential as a kind of multidimensional generalization of the inverse Gaussian distribution. And be careful, because the inverse of the inverse Gaussian distribution is not a Gaussian distribution. The name is not well chosen, but it's not my fault. And also, I said that the inverse Gaussian distribution can be achieved as an eating time of 0 by the diffuted Brownian motion. Actually, Sabo and Zeng proved that we have the same thing in the multidimensional setting. It is possible to find a family of semi-martingales which satisfy an explicit SDE, such that 1 divided by 2 beta is the first eating times of 0 by this family of semi-martingales. So there is really a lot of connection between 1 divided by between 1 divided by 2 beta and the inverse Gaussian distribution. Okay, so now in the sequel of the talk, I will always assume that theta equals 1 and eta equals 0. So theta equals 1 is not really an assumption, because one can always reduce to that by a chain of variables. But eta equals 0, it is really an assumption. And I do that because otherwise the computation in the paper with Christophe would be far too much difficult. So we have reduced to the fact that eta equals 0. And so the beta potential will always have this distribution nu v w 10 with v and w, which will depend on the context on the different slides I will explain in each context. And therefore we have H beta and G beta, which are random positive definite symmetric matrices, which are linked with this random potential beta. And one can show that it's not totally obvious, but one can show that G beta has positive entries. So now I will try to explain why Gbeta is an important object, because I said that we will try to define, we have defined it on a graph, but we will try to define it on a continuous topological object. So I will try to explain why, to motivate physical. So actually, this object Gbeta is very important, at least for two reasons. Margherita explained what I will explain in a few minutes, but I think I will do that again, maybe at least briefly. So first, one can do a change of variables with this random matrix Gbeta, and we can define a field U, so that exponential of Ui equals Gbeta of I0i divided by Gbeta of I0i0, where I fixed a vertex I0 in the graph. And actually, this field U has an explicit density, which is the following one, which has been already introduced by Margherita this morning. It is quite horrible too, but one can, let me comment this density. So we have a term of local interaction here, because we have a sum on the edges. So you have a sum of the cosh of Ui minus Uj minus 1. And if Ui and Uj are very close, it means that by a Taylor expression, you have almost 1/2 times Ui minus Uj squared, which is a kind of GFF term in the density. And you have also a term here, which is the square root of a sum on the spanning trees. But by the matrix tree theorem, you can interpret it, you can see it as a determinant. So it is a term of global interaction. And when you want to understand the behavior of this field U, you have to understand, in some sense, the competition between this global interaction and this local interaction. Okay, but we began with measure, which is nu v, which was horrible, and we made a change of variable. We have still an horrible density. So why is this interesting? Actually, it is interesting because, as explained, as Margherita has explained this morning, the field U was already known before Christophe and Pierre found it, because it was important in physics, in mathematical physics. It is the H22 model with pinning at I0. So the random matrix Gbeta is strongly linked with the H22 model. To be more precise, it is the H22 model when you have integrated the supersymmetric part and the Gaussian free-field part. And there is a second reason which explains why Gbeta is important, which is that actually Gbeta can be used in order to describe the environment of the vertex reinforced jump process. So let me be more precise. I will introduce what is the vertex reinforced jump process. So it is often called the VRJP for short. And the VRJP is defined as follows. So we define it on a graph V with the weight matrix W, which has been introduced before. And it is a continuous self-reinforced process, such that, okay, it starts at some vertex I0 in the graph, and conditionally on the past, before the time S. If at time S, the VRJP is at a vertex I, then it will jump toward a neighbor J of I at rate Wij times Lj of S, where Lj of S, it is 1 plus the local times at J. So the more you went on a vertex in the past, the more probable it is in the future to go on this vertex. So you have a reinforcement in the definition of this process. And actually, there is still a link with the U field and the random matrix Gbeta, which has been found by Christophe and Pierre, which is the following one. So if you consider the discrete time process which is associated with the VRJP, so what I mean by discrete process associated with the VRJP, I mean the VRJP taken at jump times, then this process Yn, it has the same distribution as a random walk in a random environment, where the environment is given by the random Gbeta matrix. And you can also see it as a random walk in random conductances, where the random conductances are now wij, g beta of I0i, g beta of I0j. So the discrete time VRJP can be understood as a random environment with its random conductances. So I give two reasons which explain why g beta is an interesting object. Therefore, it is quite normal thing to wonder whether it is possible to define g beta on a continuous topological object. So, for example, on a manifold or in a ball, for example. But okay, it should be very complicated to do that on any manifold. So we have tried to do that on the most simple continuous topological object you can imagine. I mean, on a circle. So, okay, we will construct an object which is similar with g beta on the circle C lambda. So we fix the size of the circle. So we say that the circle has size 2 lambda. Okay, and we identify this circle with minus lambda lambda, where minus lambda equals lambda. It is topologically identified. And okay, we have an object which is defined on any discrete graph. If we want to get an object which is similar on a continuous topological object, the natural idea is to consider a scaling limit. So it's what we will do. So in order to do that, we discretize the circle. So I consider the circle C lambda n, which is a discrete circle with 2 lambda n plus 1 point, minus lambda n plus 1, etc., etc. And we put an edge between I and I plus 1 for every I. And in order to have a discrete circle, of course, we have to put an edge between minus lambda n and lambda n. And in order to define the random matrix g beta, we need weights. So we define weights on the discrete circle in the following way. If there is no edge, we put 0 as a weight on the edge. And if there is an edge between I and j, I mean between I and I plus 1, we put the edge, we put the weight n. So the weights are going to infinity because they are equal to n, and we will make n go to infinity. And so now we have a graph, a discrete graph, and a weight matrix on this graph. So it is possible to define a random potential, random beta potential on this graph with the distribution nu c lambda n, w n lambda. And thanks to this beta potential, we can define the random matrix h beta lambda n, which is 2 beta minus the weight matrix w n lambda. Okay, and we can also define the inverse g beta lambda n of h beta lambda n, because we know that almost surely, by definition, h beta lambda n will be positive definite. Therefore, we can define its inverse g beta lambda n. Okay, and the idea would be to consider a scaling limit for g beta lambda n. So, in order to do that, we rescale g beta lambda n in the following way. So we have defined in this way a random function on c lambda squared, which is g beta lambda n of nt and t prime for t and t prime in the circle. But for technical reasons, it is easier to manipulate continuous random function. Therefore, we consider the g tilde beta lambda n, which is a random continuous function, which is an interpolating continuous version of the rescaled g beta lambda n random matrix. Okay, and of course we want to find a limiting object, a limit for g beta tilde lambda n. Okay, so in order to describe the limit, I have to introduce a continuous random kernel. So let me consider B a Brownian motion on the real line, such that B of 0 equals 0, almost surely. And we define the geometric Brownian motion M on R, such that for every t, mt is equal to exponential of bt minus t divided by 2. Okay. And we introduce a knowable process, which is the following one. Don't try really to understand that, it's just that okay, we define a symmetric random kernel G lambda on C lambda squared, which is a complicated functional of the geometric Brownian motion. And then with this definition, we have a convergence result with Christophe, which is the following one. For the topology of uniform convergence on C lambda squared, G tilde beta lambda n converges in law toward G lambda. So in this way, we have defined a symmetric random kernel, which is the natural object which corresponds to G beta, but on the circle. And okay, yes. So we have this convergence result on the circle, but let me do a small remark on the fact that this proof relies strongly on the fact that we are on the circle, because we used in the proof a small lemma, which is actually very, very important, which gives a good description of the beta potential on the circle. Indeed, if I consider a family of IID inverse Gaussian random variable on the discrete circle with parameters 1, n, I can define beta I on every site I such that it's equal to n divided by 2 times ai plus 1 over ai. And if I define the beta potential like that, it has a good distribution. It has really the distribution nu c lambda n w n lambda. Therefore, we have a simple description of the beta potential on the circle thanks to IID inverse Gaussian random variables, which is very useful actually in order to make the computations. And because when you inverse h beta, you will have you will see product of IID inverse Gaussian random variables and things like that. So it is very useful, and actually this construction is not true on any graph at all. So it is very specific to the circle. Okay, so I have defined the limit of the random matrix as a continuous symmetric random kernel, but in order to describe this limit, it will be easier to consider it as a self-adjoint operator. So now G lambda, the continuous limit on the circle, will be seen as a self-adjoint operator in the following way. We consider the kernel operator, which is associated with G lambda. So for every function f in L2, I define G lambda f of x, which is just the integral of G lambda xt ft dt. And the question is that, what can we say about this operator G lambda on L2? So in order to describe this operator, I have to introduce some horrible domain. Okay, so it is domain of h lambda, so I have not defined h lambda for now, but I will define it in a few minutes. So d of h lambda, it is just function g in L2, such that g divided by m, the geometric motion prime, is in L2. So when I put prime here, I mean the derivative in the sense of the distributions. And I also assume that M2G, the feasible quantity M2G M prime is in L2. Okay. And I add also a periodic boundary condition. So it is quite complicated, but we can understand it only as a kind of Sobolev space, which has been twisted by the geometric Brownian motion, actually. And now we have everything in order to describe G lambda. So we prove the following thing. First, G lambda is injective, actually. Moreover, the image of G lambda is exactly d of h lambda, almost surely. And therefore, it is, G lambda is a bijection from L2 onto d of h lambda. Therefore, one can consider the inverse of G lambda, which will be called h lambda. And which is defined from d of h lambda onto L2 of minus lambda lambda, so h lambda will be surjective. And let me comment that because it is a little strange, because at the beginning I first defined h beta, then I inversed it in order to define g beta. In the continuous setting, it is the contrary. I first define g lambda, and then I inverse it in order to get h lambda. But when one thinks about that, it's not so surprising, because the h beta was a kind of Anderson model. You had basically minus Laplacian plus a potential which was random, so it is a very irregular object, and it is often very complicated to consider a limit in this kind of very irregular object. On the contrary, G beta is a kind of resolvent, as it is the inverse of H beta, so it is far more regular, and it is easier to consider the scaling limit for that. So it's why we first took a scaling limit for G beta, we get G lambda, and then we inverse it in order to come back to something which is H lambda, which is an equivalent to H beta on the circle in some sense. And moreover, we have an explicit description of G lambda, of H lambda, sorry. For every G in the domain D of H lambda G is this differential function of G. H lambda it can be seen as a differential operator, and it is well defined because G is in D of H lambda. So it is not defined for every G in L2, of course, but because M is very irregular, it's not differentiable at all. But it is defined for function G in D of H lambda. And moreover, with this domain and this expression, H lambda is a positive self-adjoint operator. One can also study the spectrum of H lambda. So if I fix a positive number E, H lambda, one can show that it is compact because basically it is defined on a compact set. H lambda will have a finite number of eigenvalues between 0 and E. And so one can define n lambda of E, which is the density of states of H lambda at E. And one can wonder whether one can say something about n lambda of E. And surprisingly, yes, one can show a convergence, which is that n lambda of E divided by 2 lambda, so the size of the circle, it converges when lambda goes to infinity in probability towards square root of E divided by P. And I have to mention the fact that square root of E divided by P, by pi, it is also the density of states of minus Laplacian. So it looks like, in some sense, when lambda is very, very large, H lambda looks like minus Laplacian from a macroscopic point of view, because if you look at the microscopic scale, of course, you have the randomness, and this is a very different object, of course. Okay, so it is what I wanted to explain, so I have to mention some open questions. So the big question is it possible to do that on other topological objects? So actually, it will be far more complicated, but maybe it is possible to do it, but with other methods, of course. Can we define H beta on R as a self-adjoint operator? I think we are, because there is a question of finding on R the good domain in order to have something which is self-adjoint. And this domain is random, so it's quite complicated, but I think we are very close from being able to do that. There is also a paper, a sequence of papers of Dumas and Labbé, which studies the continuous Anderson model, which is a minus Laplacian plus a white noise. And in this sequence of papers, they are able to describe very precisely the form of the eigenstates of the continuous Anderson model, the form of the form of the eigenstates. And the question is that can we do that with H lambda? We didn't try, but maybe it is possible. And there is also a question, is it possible to construct a VRGP which is associated with G lambda on the circle? Actually, it has been done on R in a paper of Lupus, Sapo, and Tares. But on the circle, it seems to be more complicated. Okay. So I thank you for your attention.
Okay, questions?
With this Wij, G beta, I0, I0 J, why is it not the ratio? Why is it not the ratio?
Oh, it is a ratio when you consider the jumping weights. But here I was looking at the discrete time process.
Ah, okay.
But yes, when you consider just the continuous time VRGP, yes, you have the ratio, yes.
So in the continuum, are you able to write down the distribution of the beta then?
Where?
So and what was
yes, beta has vanished, actually. So now we have the operator H lambda as a differential operator, but we cannot see beta anymore. Actually, it is possible to define H, it is possible to define G, but beta in the continuous topological space, it seems that it is not possible to define it. Yes?
Maybe you could say that at a very rough level, beta is more or less the second derivative of the Brownian.
Yes, in some sense you can.
Compared to Dumas and Labbé, where they look at the white noise, it would be the first derivative of the white noise.
Yes, you can differentiate that formally, and you obtain something which should be beta, but it is very, very irregular. Actually. So it explains why it is not possible to get a scaling limit directly with H beta, because it converges towards something which is very irregular. and which makes sense only for the function g which are in D of H lambda.
Okay, any other question? If not, let's thank Valentin again.